All right, so continuing on here, part 2 of lecture 2 here, we're talking about trying to find the pressure change within a column of fluid here. And so to do that, we're just going to analyze this cube. We said this cube has an x dimension x, very simply. Left to right, we'll call that y. So let's say the box is x deep, y wide, and then we'll call it z tall. Again, I like to cross my z's, put a little cross on them. If I don't, they tend to look like 2's, and 2z becomes 4, and I lose lots of points on a differential equation test that way. And yeah, so I never I never write z without crossing it ever again. So I've got a box here, dimensions x, y, and z. We've got P1 applied on top, P2 applied on bottom. We want to know what is the difference between those two. And we're going to draw a free body diagram. That means I need to isolate or identify all of the forces acting on this box of air. Well, pressure in and of itself is not a force. And here I just want to draw forces acting on the box. So what I need to do to make this a force, this is P1, I need to make P1 or multiply P1 by the area of the face that P1 is being applied on because it's applied across this entire area. This entire area has a width X or I'm sorry, a width Y and a height or a depth in this case, X. So we're going to say P1 times XY. That is going to be this force pushing down on the top here. And then same thing from the bottom, pushing up from the bottom on the bottom face has an area XY. So I'm going to push P2 XY is going to be the force going up. And I'll say, okay, what other forces are acting on this box? Well, some people, maybe you just came off physics recently, will recognize, well, this box has its own weight, W. Yes, yes, it does. All objects on Earth's gravity are going to have weight, or on any planet's gravity are going to have some weight. So there's weight there. Yes. Other forces. Well, you've got forces in the Y direction and forces in the X direction pushing on. I've got 4 additional faces going around here, one in the back and 1, 2, and then one on the side, 3. So 4 total faces. So I've got forces pushing in all directions. That pressure is pushing in all directions. So what I'm going to do is I'm going to draw a force pushing this way in basically kind of the negative Y direction. I don't know what the pressure is. I'm just going to assume that I could just average between these two pressures. And we're going to see it doesn't really matter. So I'm just going to average between those two pressures. Again, pressure itself is not a force, so I need to multiply by the area here. Well, this area, it's z tall, x wide. So I'm going to multiply by xz to get that force. That's the area the pressure is being applied to. And again, I don't know the pressure over here. I'm just going to assume that I can average it. And we'll see in a little bit here that it really doesn't matter what I call it. So I'm going to average between pressure 1 and 2, call that the pressure. And again, pressure is not a force. I need forces here, so I'm going to multiply by the area xz to get a force. So I've got in the positive and negative y direction, the average pressure times the area of the face, xz. And the same thing from these sides. Right? Going into and out of the page, I've got, again, I'm just going to call it this average pressure, P1 plus P2 divided by 2. And the area of this face, it's Y wide and Z tall. So it's going to be YZ is the area of this face. So the average pressure times YZ. And the same thing back here. The average pressure, P1 plus P2 divided by 2 times YZ. Okay. Now, I'm going to write one big long force equation here, one big long vector equation. So I'm going to call this is going to be lecture 2. This is page 1 of something. Keep me organized when I do that. All right, so I've got my free body diagram here. Let's see, I've got just enough room. I think I can write my force vector equation. You can break this out in x, y, and z components if you like. I'm going to assume Newton's first law applies here, and this box is in equilibrium. let's just assume that it's stationary, that all these forces are going to cancel out. I think that will allow us to solve what we need to do here. So in the x direction, that's into and out of the page, I've got this average pressure, P1 plus P2 divided by 2, and that's times the area YZ. I've got it in the positive x direction coming out here, and the negative x direction pushing into the page, minus P1 plus 2 over 2 YZ. Both of those are in the x direction, so we'll multiply by the I vector. That's the unit vector in the x direction. Add to it then in the y direction, I've got in the positive y direction pushing to the right here, again, this average pressure, P1 plus P2 over 2, and that one is times xz. And then I've got the same thing in the negative y direction pushing to the left there, P1 plus P2, both over 2 times xz. Those are in the j direction. And then finally, in the k direction, I've got P2 going up. It's positive y. I've got minus W and minus P1 all in the k direction. Now, you don't have to, don't worry. If it's like, Steve, I don't know anything about three-dimensional statics problems. That's fine. It's not required. I'm hoping I'm drawing on your being able to draw a free body diagram at least in 2 dimensions. Maybe it's some basic vectors in your physics class, if not maybe a calculus class. Don't worry. This is the last time we're going to do IJK vectors. But what I wanted to do is just show you the point that we acknowledge that I've got equal and opposite pressure in the x and the y directions that are just going to cancel out. So what I end up with then is I have zero force in the x direction, zero force in the y direction. All of the force then is in the z direction. Right? So I'm going to ignore the x and y now. I'm just going to say, well, let's just add up the forces in the z direction. That's equal to 0. 0 is equal to P2 minus W minus P1. Where did the k go? Well, 0 divided by k is still 0. So, because k is just 1. So what does that mean? P2. Oh, you know what I did? I apologize. This is P2. Remember, I've got XY. I apologize. I made a mistake. That happens sometimes. Remember, I've got up here XY and XY. I didn't include those up here. I was trying to save space and squeeze it all in there. P2XY minus W minus P1XY times K. Now, everything else I said still applies. We're just going to look in the sum of forces now in the z direction because I've got 0x and 0y. So sum of forces in the z direction equals 0. P2xy minus W minus P1xy. That's going to be equal to 0. Perfect. So if I group these together and say, well, P2 minus P1, both of those are times xy, that's going to equal the weight. Okay. How would I find the weight of this box? Right? That's what that W, the weight represents, is the weight of this box. So how would I find the weight? Well, you'd find any weight just simply as mass times gravity. Right? Well, I got this box here. How do I find its gravity is known? That's just depending on the planet we're on. How do I find its mass? Well, and these are questions I would ask in class. And so you can kind of pause here and think about philosophically, how would I find the weight or the mass of this box? And then I would normally, again, I would pause and kind of wait until somebody starts giving me answers. And normally somebody would come up with, well, can't you just, if maybe you know the density of the fluid, the density times the volume is going to give you the mass. And I'll say, okay, well, that's good. Let's say it's air or whatever the gas is or the fluid is. We can find the density that way. How do we find the volume, right? And how do we find the volume of this box with dimensions X, Y, and Z? Well, and I try to seed that a little bit. And normally somebody says, oh, well, that's volume is X, Y, Z, just It's a box, so you just multiply those dimensions together. Yes. So notice what we got here. X and Y are both non-zero, so they're on both sides of the equation. They can just cancel out. P2 minus P1 is equal to the density of the fluid times gravity times a z value. And normally what we do is we write it this way. It's actually a difference in z's, and your text and modern texts write it this way. P2 minus P1 is equal to rho g z1 minus z2. That's where this z value is referring to elevation, meaning z is going to increase as you go up, right? So if I go, basically in this case, I'll be going down, so I'll have a lower z value down here than I did up here. So I'm going to a lower z value, which means my pressure is going to increase. So if I decrease my elevation, right? If Z2 is smaller than Z1, if I'm decreasing my elevation, I'll see an increase in pressure. And vice versa. If I go up in a column of fluid, I'll experience less pressure. So if I increase my elevation, I will get a negative value here, right? So if Z2 is the larger one, I get a negative value, meaning my pressure will drop as I move up in the column of fluid. Right? So kind of wrestle with that a little bit. Some texts, you'll encounter some texts, they'll say P2 minus P1 is equal to rho G delta Z. So delta P is equal to rho G delta Z. And that's okay if you want to remember you're referring to Z as depth, right? So if Z is what you're calling the elevation, then it needs to be Z1 minus Z2 if Z is increasing in the up direction. If Z is referring to depth, meaning Z increases as you go down, well, if you go down, your pressure is going to increase. So if Z is increasing in the down direction, that means your pressure is increasing in the down direction. Whichever way you want to keep track of it, your text likes to use Z referring to elevation because we will also use Z to refer to potential energy, for example. And so with potential energy, your potential energy is going to increase as your elevation increases. So we can use the same Z value here in this equation as we can in potential energy if I'm using Z to refer to elevation. So that's the reason your text does it. And it took me some time because I was actually taught this way. Delta P is rho G delta Z. And so it took me a little while to kind of get used to this mentality of, no, let's call Z elevation. But your text does that, and I try to be very consistent about that. Okay, either one works. So I'm going to go back to my PowerPoint here. Getting close to the end of this video. Nope, back. I apologize. P2 minus P1 is equal to the density of the fluid times gravity times Z1 minus Z2, where here we're referring to Z as elevation. That means Z is going to increase in the up direction. So basically what you have here is that this essentially represents the weight of the fluid. So as you move down in the column of fluid, you have more weight of the fluid piling on top of you, meaning you have more pressure on top of you. So again, if you go to the deep end of a pool, or if you go diving at all, you experience this, and this is what's happening. Again, you have the weight of all the fluid molecules on top of you, pushing down harder as you move your way down. All right, I'm going to stop there. I've got to get me some water. I'm just about at my 15-minute mark. We'll pick up there next time looking at how we can apply this.